Okay. Today we study these three topics. Let me finish this topic from the last class, fundamental theorems that we often use, and then compute a polynomial from section 1.2. I skip chapter 2 and jump to 3.1. Bisection method for the solution of a nonlinear equation. Okay, now topic 1. Several theorems that we often use. Theorem number 1, intermediate value theorem. Intermediate value theorem. On a closed interval. On a closed interval AB, a continuous function f can assumes all the values between function value at the two endpoints. This is from the last class. The second theorem, number 2, mean value theorem for derivative. We also have a mean value theorem for integrals, derivatives. If function f is continuous on a closed interval and derivative exists everywhere on the open interval AB. The second condition says that the graph has no corner. In other words, smooth. Then, conclusion. There is at least one point sign in the open interval between A and B, such that derivative as sign, derivative is slope of a tangent line. There is a tangent line whose slope is equal to f of b minus f of a, then over b minus a. This fraction is the slope of the line that joins the two endpoints of the graph of the function. So mean value theorem, this theorem says that there is a tangent line guarantee that is parallel to the line that joins the two endpoints of the graph of function f. Now, next theorem, a special case of mean value theorem. Theorem number 3. This theorem is called Rolle's theorem. special case of theorem 2. If function f is continuous on a closed interval, derivative exists on open interval, and one more condition: function value at A is equal to function value at B. Function value at A is equal to function value at B, then this number is equal to 0 because f of B minus f of A is 0. Now, conclusion is then there is at least one point psi between A and B such that slope of the tangent line there is 0. Slope is 0, tangent line is horizontal. Okay. Rowe's theorem. Now, the fourth theorem, mean value theorem for integrals. Theorem number 4, we often use mean value theorem for integrals. This theorem says that let U and V be two functions, be two continuous functions on a closed interval AB. And suppose function V greater than or equal to 0 over this interval. Function value everywhere non-negative. Now, conclusion. Then there exists a point psi in this closed interval. Closed interval. That means that psi can be A, left endpoint, B, right endpoint, or between A and B. Such that integral from A to B, U of x, V of x is equal to, we can move U outside the integral. U evaluate at point psi times integral A to B, V of x dx. Yeah, let me present the proof of this theorem. Proof, not difficult. Two cases. First case, case 1. Function B greater than or equal to 0. Case 1, function B is everywhere is 0. In this case, then this equation clearly is true. Let me call this equation 1. Clearly is true. Why? Because left side left is okay. Now V is 0. So left side is A, B, U times 0. So this integral is 0. Right side is equal to, no matter what side is, arbitrary pick a point for sine. U sine integral 0. Integral is net area between the graph of the integrand, the function, and x-axis, and between A and B. So this is this case area integral is 0. So sine times 0 is 0. So this case clearly is true. Now second case. Case 2. Okay. V not equal to 0 everywhere on the interval AB. Yeah. Say for example, let me draw a possible graph of V. Okay. A, B. V non-negative, and at least at one point, function value greater than 0 and also continuous. So the graph, say suppose somewhere greater than 0. Therefore, this integral A to B integral on V. This is an area between the graph of V and x-axis and between A and B. Clearly, the area from this diagram, you can see that this integral must be positive number. Let me denote this integral by say I. Okay, I is this integral. I greater than 0. On the other hand, U is a continuous function on the closed interval AB. So U has maximum and has minimum on the interval AB, right? That is extreme value theorem in calculus 1. Less than say beta greater than alpha for x in AB. A beta maximum function value, alpha minimum function value. Now, multiply the free terms of these two inequalities by function V. Function V non-negative. So because of V non-negative, when I multiply all the free terms, I don't change the inequality direction. If you multiply a negative number, then you need to change the inequality direction. So multiply V to alpha, multiply V to U, multiply V to beta. Okay, inequalities have the same direction with these two inequalities because V non-negative. Okay, now alpha V less than equal to U times V, beta times V. Now I take integral on these two inequalities, then I get integral AB alpha V x dx integral AB U x Vx dx less than integral AB beta Vx dx. Okay, now I move out the constants alpha and beta outside integrals. Then I get alpha times this integral less than or equal to U V integral beta AB integral. Recall that I use I to denote this integral. So therefore, I have alpha times I less than or equal to integral U times V dx less than or equal to beta times I, a positive number, right? Greater than 0. I divide the inequalities by I, positive number. Then I get this. Over I, beta. Yeah. So this number, this is a number. This number is a number between the minimum function value of U and the maximum function value of beta by intermediate value field. By intermediate value field. A continuous function assumes all the values between the two endpoints. You can extend the theorem to a continuous function can assume all the values between minimum and maximum. So therefore, there is a point psi in the closed interval such that this number between maximum and minimum is equal to U of psi. Now, last step, move I to the right side. Then we prove the field is a U psi I. I is integral AB on V. The proof is not difficult. This is topic 1. I finished the topic from the last class. Now, second topic from section 1.2. Compute a polynomial. There is a popular algorithm. The algorithm, its name is Horner's method or symplectic division. Topic 2. An algorithm to compute a polynomial. Consider this polynomial, a general polynomial. Degree is n. A second term, a n minus 1, x n minus 1, and an minus 2, xn minus 2. The third last term is this second last term. And the last term, A0. Now the question is, here x is assumed to be some number. I evaluate the polynomial at that number. X is some number. And now, how to efficiently to compute the function value x sum x? Efficiently means we want to minimize the number of floating point operations. The idea is write the polynomial in a nested form. Originally, this idea is from Horner. From Horner, this mathematician. Okay, take a look and the terms, all the terms except the last term. We can see that x is a common factor. Factor x out. Factor x out. Then we have an xn minus 1 plus an minus 1 xn minus 2 an minus 2 n minus 3 because 1x is out. The third last term will be a2x plus the second last term a1 times x plus a0. And continue to factor x out. Now within the curve brackets, consider all the terms except the last term, a1. Then take x out. An 1x is out, so n minus 2 plus an minus 1 x n minus 3, then an minus 2 x 1x out, n minus 4, and a2 x is out, so times x plus a1 times x plus a0. Continue the factorization. Within these two curve brackets, consider all the terms except the last term. And take x out, then we have an xn minus 3 plus an minus 1 xn minus 4 and an minus 2 minus 5, then plus the second last term is a3 times x plus a2 times x, then a1 times x plus a0. Continue the factorization, and then finally we get we written the polynomial p as here. an times x plus an minus 1, then times x plus an minus 2 times x, and so on. A3 times x plus a2 times x plus a1 times x a0. Yeah, let me show you one example. Say, for example, write this polynomial. The degree is to the fourth. Degree is 4. x3 6.1 times x squared, and then say 3.2 times x plus constant term 1.5. In a nested form. Solution. P is how many terms? 5 terms. Now consider the first 4 terms. Take out x times x 1.5. Within the parentheses, consider the first 3 terms and take x out. Then we have x squared plus x minus 6.1, x plus 3.2, x 1.5. Now, consider the terms within this pair of parentheses. The first 2 terms, take x out. Then we have x out times x minus 6.1. How about I use square brackets here, and then 3.2, and here, how about let me use curve brackets, x plus 1.5. Yeah, done. Okay. This is the polynomial in nested form. Now, let me compute this polynomial now. Okay. Okay. Computation. Compute. Okay. Compute. Okay. First, compute x plus 1 and store the result in P. Now, P is x plus 1. Then compute P times x. P times x minus 6.1 and store the result in P. Now, P is this number. Now, next, P times x plus 3.2. P times x plus 3.2 and store the result in P. Now, P is this number. Finally, compute P times this x, then plus 1.5 and store the result in P. Then this P is the value of this polynomial at the number x. How many multiplications for this computation, P here, there is a P times X. So 1 multiplication, 2 multiplication, then 3. So to compute the function value, we need 3 multiplications. And summation subtraction in total is 4. So I think 3 multiplication is the minimum number of multiplications to compute this polynomial and X. This is a well-known algorithm. Okay, algorithm. The algorithm. Let me present the algorithm to compute a general polynomial. The algorithm is called Horner's method, or symphatic division to compute a general polynomial. The algorithm reads: step 1, store the leading coefficient in P. Okay. Then step 2, run a for loop K from n-1, n-2, n-3 until 0. X times P plus AK, then store the result in P, then N. Then how to understand this algorithm? I suggest step by step. When K is n-1, then this new P, what is this new P? This new P is X times the OP is AN plus, now K is n-1, so AN-1 when K is n-1. Okay, after then this new P, what is this new P? Go back to here. This is the polynomial P in the nested form. So when K, after K is n-1, actually we have compute this number. This is a P. This P. Now K is n-2. K is n-2. Then implement this 9. This 9 becomes P X times P plus, okay, now K is n-2. Now go back to the nested form. Remember, this OP is this number. Now the new P will be this number. New P will be this number. Okay. So when K is n-3, run this 9. Now K is n-3, AN-3. Then this new P is the number here. The number here, AN-3, and so on. When K is 0, then we get the value of the polynomial. Yeah, to compute the value of a polynomial, usually we use corner method very fast. Yeah, this method minimizes the number of multiplications. This is a second topic. Topic 3. Topic 3 is about chapter 3. Chapter 3, this whole chapter is find the roots or zeros of general nonlinear equations. Bisection method. Okay, bisection method. Yeah, topic 3. Section 3.1. Bisection method. Sometimes we call this method interval halving method. Cut interval in half. In chapter 3, this whole chapter, we want to solve equations, nonlinear equations. Say f of x is equal to 0. F usually nonlinear, a general function. And we want to, this is a single equation. We also solve a system of equations. And we want to solve a system of equations. Say f1, x1, x2. How many unknowns? For example, n unknowns is 0. A system, okay? A collection of equations. F2, x1, x2, and xn is 0, and so on. How many equations? At least n equations. N equations, n unknown. We can determine the unknowns. So Fn, n equations, n unknowns. This is what we want to do in chapter 3. Now, bisection method. Bisection method handles a single equation. Bisection method. Okay. Solve a single equation. Of course, we need some assumption about this equation. Okay, assume. Okay, we just assume. Okay, A function f is continuous on a closed interval. Continuous. Assume function value at left endpoint times function value at right endpoint less than 0. That means that function value at the two endpoints, the values have different size. Okay. Yeah. If you draw a diagram, A, B, function value at the two endpoints, the product less than 0. Say, for example, function value at A, suppose positive. Function value at B must be negative. Now the graph continuous. So by intermediate value theorem between A and B, they must be a root or a zero to this equation by intermediate value theorem. A root, R, right? So we want to find a root, okay? The idea of bisection method is cut the interval AB each time by half, in half, okay? Let me draw a diagram about a general function. Yeah. X and Y. Suppose A here, B is here. Function value at A is this point. A general function. Function value at B is this point. Okay. Now, the bisection method, the basic idea, bisection method. Okay. Number one, compute the midpoint of the interval. Compute midpoint, central point, A plus B over 2. Yeah, midpoint here. A, B. Now, cut C is here. Okay, step 2. Test compute function value at the midpoint. Then test function value at A times function value at C. Okay, test if the product less than 0. If A, there are some cases. If this inequality is true, A times function value at C less than 0, it is true. Then function has a 0 in the interval AC, right? Yeah, just like this case, this is true. Function value at A positive, function value at C negative. Yeah, this case satisfies this inequality. So there is a 0 here inside the interval AC. Okay, now we have interval AC. Now set a new interval AB to AC. Okay, now we rename this point B. Then we have a new AB, but this new AB smaller, but still contains a root, a 0. Okay, 0. Okay. Hey, how about second case? B. If this inequality not less than 0, in other words, greater than or equal to 0, okay. Then also there are 2 cases. Okay. Case 1. Okay, case 1. Function value at A, we assume non-zero. So case 1 is f times A. F of A times f of C is 0. Yeah. Function value at A times function value at C greater than or equal to 0. Also, there are 2 cases. The case is equal to 0. Then because f of a belongs 0, we must have function value at c is 0. Then c is a 0. Done. If this case is true, then done. But this case, in real life computation, this case usually doesn't happen. Why? Because of round-off error. The chance to exactly get f of c is 0, the chance is very poor because of round-off error. Now, second case, f of a times f of c greater than 0. Second case, f of a times f of c greater than 0, then this implies, because we assume function value at a, function value at b, they have opposite sign. Now, function value at c times function value at a greater than 0. That means that function value at c has the same sign with function value at a. Therefore, this inequality implies that function value at c times function value at b less than 0, must be less than 0. So there is a root in this interval c to b. Now, in this case, we rename the point c as a. Then we also have a new interval ab. But this new interval ab is half the length of the original interval ab. Right? Yeah, this is the idea. Okay. Okay. No matter what case will be, in either case, a new interval AB that contains a 0. Usually I use 0 or root. Use R. Okay, of function f has been produced. Okay. And this new interval in length half the length of the original interval. Okay. After we have a new interval, then repeat the same step. Cut this new interval in half, then test function value. Okay, at left endpoint, midpoint, and right endpoint to determine, okay, which half of this interval still contains the root. So this process, okay, is repeated again and again until the new interval always contains a 0, until the new interval small enough. Okay. In bisection method, we always use the midpoint of the interval AB as we always use the midpoint of the interval AB as an estimate of the 0 R. When this interval AB is small enough, the midpoint and the root. Remember, always inside this interval. So when AB is small enough, the distance between the midpoint and the root is always less than the length of the interval. Actually, half of the length of the interval, B minus A. Why half? You see here, AB, midpoint C, arrow here. So distance between arrow and C always less than the half of the interval, the length of the interval AB. So when B minus A is small enough, C is close enough to the root that we want to find. And C is considered to be the solution.